the Doppler effect and shock waves. Have you ever heard a police car or a fire engine or an EMS truck approaching and passing you? What does a siren sound like? So here's one person. Police car is going towards this person, and it's going away from this person. Perhaps you notice that the pitch or the frequency changes as the police car passes. It is higher when it approaches you, okay, and it is lower when it's going away from you. So this kid here hears a lower frequency. This kid hears a higher frequency. That's the Doppler effect. It's the change in frequency of a wave for a wave source that is moving relative to an observer. You're the observer, the wave source is the police car. What's happening is that the waves look different on the left and right side of the police car as it moves towards the person in the blue shirt. The waves here are getting closer. Why? Because the police car is actually trying to catch up with them. He's not going to do it because they're moving at 340 meters per second, which is a lot faster than the police car can move. But the waves are, you could say they're piling up in front of him a little bit. Now, the waves behind him, he's leaving them behind, so they're spreading out a bit more. That leads to a high frequency here, which is going to be a small wavelength because they're inverse. Here you have the low frequency and a long wavelength. Here's a nice video on the Doppler effect. When a sound source is stationary, the sound waves move outward in all directions with equal wavelengths. And that's what we're showing here with all these circles. This is the sound source and it's not moving. Here's the observer. And the observer at the moment is not moving. If there is zero relative velocity between the source and the observer, that means they're not moving relative to each other. Each one sees the other one stationary. The observer will hear a constant frequency corresponding to the equal wavelength. So here's a little math here. V relative is going to be the velocity of the source, the sound source, minus the velocity of the observer. If they're both not moving, there is zero relative velocity. Now we set the sound source in motion, moving to the right. That was the police car in the example we had, right? Moving source has a velocity v sub s. It's kind of catching up with the waves that are produced and moves away from the waves over here that are moving to the left. Remember, the source is always emitting waves in all directions. But if he's moving this way, he's trying to catch up with these, and he's moving away from these. So how are the waves different on the left and right side of the moving sound source? Well, the wavelength has changed, both in front of and behind the moving source. Let's look at the wavelength here now. Behind, it's that length, right? In front of him, can you see how it's a lot smaller? So here you have a smaller wavelength. And what does that mean for the frequency? It means the frequency is higher. So the pitch frequency heard by the stationary observer increases. A stationary observer to the left sees these longer wavelength waves, okay, which means it has what? A smaller frequency, a lower pitch.